Hi, everyone. My name is Aaron Pina, and I'm a Deputy Program Scientist in NASA's Earth Science Division. In NASA's Earth Science Division, we study nearly everything in the Earth system, from the top of the atmosphere to deep underground, including oceans. NASA's Earth Observing System Data and Information System, which stores data from Earth-facing satellites, has over 33 petabytes of accessible data, or equivalent to 67,200 years of uninterrupted MP3 music. Artificial intelligence and machine learning are useful to help extract patterns and knowledge from large data sets that will accelerate our geophysical understanding of Earth's processes. In one project I would like to introduce, we have the Earth Intelligence Engine project being led out of MIT. This project uses machine learning to generate photorealistic images of coastlines after flooding, especially from a tropical cyclone. A project like this is of particular interest to emergency managers from the federal to local levels. This is also of interest to programs at NASA, such as the Disasters Program in the Earth Science Division. In another project I'm introducing, we have a lightning study being led by partners from Lockheed Martin. This project uses data from a lightning sensor on a satellite 36,000 kilometers away. This is the equivalent to starting in Eastern Africa and going all the way around the globe and ending up in Western Africa. This geostationary satellite is fixed on looking at North and South America, as well as the Atlantic Ocean. Understanding how lightning impacts severe storms can help improve the predictability of storms. This type of work is of great interest to communities across the globe impacted by severe weather. So without further ado, I'd like to introduce the teams.
Hello, everyone. We are the Lightning and Extreme Weather team. The four researchers on our team are Yvonne, Merrick, Nadia, and myself, Maria. Our four team members or mentors include Mark, Clem, Samantha, and Greg Renard. We would also like to acknowledge Benny, Adwait, and Greg Sine for their contributions to our work. During the evening of April 22nd, a tornado moved across Southeast Texas. This tornado had maximum winds estimated to be 130 miles per hour, lasted over 45 minutes, and carved a path of destruction 37 miles in length. The damage path was so substantial that it could be seen from space. Here's an image of that path. Severe thunderstorms can produce hazards that include tornadoes and large hail, which can claim lives and cause substantial economic damage. The cost associated with the cost and societal exposure associated with severe storms has been increasing in recent years, and this makes it that much more important to continue improving our understanding and predictions of these storms. During severe thunderstorm events, forecasters are under pressure to issue warnings that can alert the public of imminent danger. Forecasters have a large amount of physical model output and observational data to analyze, but very little time. Now, Merrick will introduce how our project aims to help forecasters.
Our challenge is to use geostationary satellite observations for short-term predictions of severe weather. Forecasters ingest an enormous amount of information and utilize their domain knowledge and experience to issue warnings. We aim to build a tool that can help forecasters identify the storms with potential to evolve into tornado or hail hazards to increase forecasters' situational awareness and be more confident in their assessments. With the recent launch of the GOES weather satellite, the geostationary lightning mapper, an optical lightning sensor, shown here on the left, now offers unprecedented continuous coverage of lightning across the Western Hemisphere. GLM captures 500 frames per second and sees about 1 million lightning flashes per day. Lightning occurrences anywhere across the full disk of Earth are then downlinked in nearly real time. Since lightning is a proxy for the intensity of thunderstorms, we ask the question, with the wealth of lightning observations from GLM's unique vantage point, can we use state-of-the-art machine learning techniques to skillfully forecast tornado and hail hazards? Ground-based observations of lightning have shown the utility of lightning data to aid in predicting severe weather events. In many cases, like the time series shown here, there is a spike in the lightning rate prior to the onset of a tornado or of hail. As updrafts become more vigorous, more charge separation occurs, which leads to more lightning strikes. Next, Nadia will talk more about how we use the lightning data from GLM to make predictions.
To accomplish this, we used 31 nodes to process millions of files of GLM lightning events from March 2018 through June 2020. Each file spans 20 seconds and covers the full disk of the Earth observed by the GLM. We derived several physical quantities and gridded the data into 2 kilometer by 2 kilometer bins at a 1 minute cadence. We then focused on the Great Plains of the US during the spring of 2019, where many severe events occurred. Our approach to this problem was to exploit lightning behavior leading up to severe weather events temporally as well as spatially. From the temporal aspect on the left, we transformed lightning time series such as flash rate and flash area using 10,000 random convolutional kernels, Rocket, to extract features in a single layer, which we fed into a classifier to determine the severity of an event. Spatially, as seen on the right, our approach utilized computer vision on the lightning data, augmented by cloud top temperatures from another co-located instrument on the GOES, the Advanced Baseline Imager. Spatiotemporal patterns were then examined using video frame prediction techniques based on recurrent neural network structures embedded within a two-dimensional ConvNet architecture. While some initial results are shown, I'll hand it over to Yvonne to discuss the results of the GLM time series classification.
We use two well-known metrics in the atmospheric science to assess the skills of our models: the critical success index and false alarms ratio. Both metrics are defined based on the 2x2 confusion matrix or contingency table. In the table on the right, we can see the skill of our model paired to the state of the art by the National Weather Service. Our results are very positive, but we must note the differences in lead time, coverage, and period. To summarize, our results are the following. We built a model with 15-minute lead time using 8 GLM quantities. In our test data sets, the false alarms for warm storms with no actual severe weather reports were reduced by 50%. In addition, in 8 out of 10 times, the model was able to classify the severe weather correctly. These results suggest we can continue to enhance and refine this work to help forecasters using lightning data. We aim to have these models tested at the NOAA Hazardous Weather Testbed in Norman, Oklahoma, firsthand by forecasters.
The April 22nd tornado of Southeast Texas moved across a rural area, so there were no serious injuries. However, we may not be as lucky with the next tornado. With GLM data and machine learning, however, we can be prepared. We'd like to take the time to extend an expression of gratitude to those who believed in us, to the Frontier Development Lab, to our mentors, and all of the key contributors to this project. Thank you for giving us the opportunity to make good science with great impact. Thank you.
Great. Thank you so much, Lightning team. This was really exciting work. And I would like to bring out our panelists once again. So this time, I'm going to ask our panelists if they can tell us one sentence about why this is important. And to start us off, I'd like to turn it to Aaron.
Yeah, so the average lead time for a tornado warning is about 13 minutes. So with this project, like this, can we improve the predictability of severe storms?
Thanks, Aaron. And now I'd like to turn it over to Rodney.
Well, this one hit home for me, having family that lives in basically hurricane vulnerable areas. And certainly having any additional lead time will be instrumental in effective in trying to take cover. The fact that the team is actually focused on false alarms and misdetection, as I think is extremely important too, because false alarms and false negatives have dramatic implications as well.
Thanks, Rodney. And Scott?
Sarah, I almost felt that I was watching weather forecast again. But what's interesting here is that you've got the atmospheric sciences. Now you blend that with sensors from NASA and new sensors from NASA, as well as the science of Silicon Valley. And those two together are doing things that in a few years we'll expect to see forecasts for where lightning and storms will be happening, and hopefully get ahead of those terrible things we talked about, that long stripe that took out all that area in Texas. So I really look forward to them bringing this back into mainstream, see it on broadcast TV.
Yeah, same here, Scott. Colorado has a lot of severe weather, so definitely would love increased warning time. So with that, I'd like to thank the Lightning team and our panel, and I'd actually like to send it over to Deva from MIT to give us a few words. So